What if 95% of the universe, dark matter and dark energy, doesn't exist, but is instead an illusion? A new study from the University of Ottawa suggests the effects we see are caused by subtle changes in the very laws of physics over time. This challenges the bedrock of cosmology, proposing a single evolving equation can explain galaxy rotation and cosmic expansion, replacing two massive mysteries. Let's explore this together. The dark matter dilemma. For nearly a century, we've built our entire model of the cosmos on two phantom ingredients. Here's what matters for decades. Modern cosmology has rested on the assumption that about 95% of the universe is composed of dark matter and dark energy. We can't see them, we can't directly detect them, yet their influence seems to explain everything from how galaxies spin to why the universe is expanding faster and faster. Think about the flat rotation curves of galaxies, where stars, on the outer edges, move just as fast as those near the center, defying the visible mass we can account for. We attribute this to the gravitational scaffolding provided by dark matter. Then there is the accelerating expansion, blamed on dark energy. Professor Rajendra Gupta is challenging this entire foundation. He argues that this framework, which relies on these invisible components, might be entirely unnecessary. The core problem as he sees it is that our universe model requires these two separate mysterious entities to make the math work, and that complexity might be a sign we're missing a simpler, underlying truth. Bottom line, the current model, known as lambda CDM, is incredibly successful, but relies on these two unknowns making up the vast majority of everything. Gupta is trying to remove both unknowns with one elegant change. Gupta's challenge. So, how does a single researcher from the University of Ottawa dare to challenge a paradigm supported by decades of data? Here is what matters. Professor Gupta is not simply guessing, he is proposing a mathematically consistent alternative to the established lambda CDM model. He accepts the observations, the fast-spinning galaxies, the accelerating expansion, but seeks a different cause. Instead of inventing two separate invisible components, dark matter and dark energy, Gupta suggests we look at the fundamental constants that govern forces like gravity. The assumption in physics is that constants, like the speed of light or the gravitational constant, are eternal and unchanging across all time and space. Gupta's research, which builds on his earlier work questioning large-scale dark matter effects, proposes the opposite. He suggests that the strength of the universe's fundamental forces may be slowly weakening or evolving as the cosmos expands. This radical idea means the rules governing gravity and other forces were slightly different billions of years ago than they are today. This is a direct challenge to the very notion of eternal physical laws, which is a bold move in any scientific field. Evolving constants. If the laws of physics are changing, what does that actually look like on paper? This is where the theory gets mathematically concrete. Instead of modifying Einstein's equations of general relativity, Gupta's model allows the parameters within those equations to shift over time. Imagine the strength of gravity is determined by a constant, let's call it g. In the standard model, g is always g. In Gupta's framework, g slowly varies as the universe stretches. This time dependence is the key mechanism. As the cosmos expands, the strength of this fundamental interaction subtly decreases or changes its behavior based on the scale. This is different from older modified gravity theories, like modified Newtonian dynamics, or MOND, which often proposed that Newton's laws break down under very weak gravity, a concept explored by scientists like Mordechai Milgram decades ago. Those theories struggled to explain structures on the largest scales like galaxy clusters. Gupta's approach is different. He keeps the core structure of gravity, but makes the governing parameters dynamic. The universe, in this view, is not a clock wound up at the Big Bang with fixed rules, but a living system whose fundamental relationships between space, time, and force are slowly adjusting themselves. The alpha factor. To mathematically capture this idea of changing physical laws, Professor Gupta introduces a new term into his model, alpha. This is the ingenious mathematical lever in his theory. This term, alpha, acts as a time-dependent adjustment factor that modulates the strength of gravity as the universe ages and expands. Here's the fascinating part. Alpha behaves differently depending on the scale you are observing. On the largest cosmic scales, where matter is thought to be distributed uniformly, this alpha factor acts exactly like a gentle, repulsive force across all of space. This is what we have been calling dark energy. Now, pivot to smaller galactic scales. Within a galaxy, where there is a high local density of stars and gas, the same evolving alpha term subtly enhances the gravitational pull in those regions, effectively mimicking the exact behavior we attribute to dark matter halos. The beauty of this approach, as Gupta sees it, is unification. It replaces two separate enormous mysteries with one single evolving mathematical principle. It posits that we are seeing two different faces of the same underlying phenomenon, the dynamic nature of our universe's laws over time. A unified explanation. Why is having one factor explain two major mysteries so scientifically appealing? Simplicity is often the hallmark of truth in physics, and this is where Gupta's model shines against the standard lambda CDM model. The standard model requires two independent entities: cold, dark matter, an exotic particle, and dark energy, a constant energy density of space. They are treated as separate problems requiring separate solutions. Gupta's evolving constants framework unifies them. It posits that one principle, the gradual time evolution of a physical constant encapsulated by the alpha factor, produces both effects. On the grand scale, it's dark energy. On the galactic scale, it's dark matter. This unification is powerful because it reduces the number of independent mysteries we need to solve. It suggests the cosmos is governed by a single, albeit dynamic set of rules, rather than an unlikely coincidence of two disparate, unknown components. While previous attempts, like those based on Milgram's Mond, succeeded on galactic scales but failed on cosmic scales, Gupta's model is designed from the outset to operate coherently across all observed structures by treating the change as inherent to the expansion itself. The beauty lies in this elegance, replacing two unknowns with one evolving parameter. Revising cosmic age. If the fundamental forces of the universe have been changing since the Big Bang, then the rate at which the universe has expanded over its lifetime must also be different from our current estimates. This leads to one of the most startling implications of Professor Gupta's work: a radically revised cosmic timeline. Our current best estimate places the age of the universe at about 13.8 billion years. However, if the strength of gravity and other constants were different, the entire expansion history changes. According to Gupta's calculations, this adjustment would imply that the universe is nearly twice as old as we currently believe, placing its age closer to 26 or 27 billion years. Why is this significant? This older age could neatly solve a major headache in modern cosmology: the puzzle of early massive structures. We observe incredibly massive galaxies and supermassive black holes existing just a few 100 million years after the Big Bang, a timescale that seems too short for structures to grow so large under the standard model. An older universe, one with slightly different physical parameters in its infancy, provides the necessary extra time for these colossal structures to form naturally, without needing hypothetical mechanisms to accelerate their growth. Alternative theories. So, this isn't the first time physicists have tried to ditch dark matter, but why might Gupta's approach actually succeed where others stalled? You know, science really advances by challenging assumptions, and the belief that physical laws are static has definitely been questioned before. Since the 1980s, alternative frameworks like modified Newtonian dynamics, also called MOND, proposed by scientists such as Mordechai Milgram, attempted to adjust gravity's laws at very low accelerations to explain galaxy rotation without needing dark matter. While MON did manage to explain many galaxy rotation curves, it famously struggled when applied to larger scales, like galaxy clusters or the overall expansion of the universe, where, often, dark matter had to be brought back into the equation. Gupta's model, though, takes a different route. Instead of modifying the laws themselves, it actually modifies the constants that govern those laws over time. That allows him to keep the framework of general relativity mostly intact, while letting the effective gravitational force change smoothly across both space and time. This framework tries to address the scale problems that plagued earlier modified gravity theories. Plus, it connects with a deeper philosophical question in physics. Are constants like the fine structure constant or the gravitational constant really fixed throughout all of existence? Gupta provides a concrete model, what he calls the evolving constants framework, to explore that very possibility, pushing well beyond the limits of previous attempts to bypass the need for dark matter. Testing the framework. The bottom line for any radical new theory is that it must face the music of observation, and honestly, the bar is incredibly high. For Gupta's evolving constants framework to gain acceptance, it must perform at least as well as the reigning champion, the lambda, cold, dark matter, or lambda CDM model. Lambda CDM is not some casual theory. It is a robust framework that has withstood countless rigorous tests, from analyzing the cosmic microwave background, the echo of the Big Bang, to mapping galaxy clustering and gravitational lensing effects. Any alternative must match that proven precision, while also simplifying the overall picture, not complicating it further. This means Gupta's model must now demonstrate how evolving constants can accurately reproduce the rotation patterns of individual galaxies, a feat that the earlier modified gravity models sometimes struggled with at scale. The challenge is enormous. The theory must show how its single, evolving equation generates the exact same results that scientists currently attribute to two separate invisible components across thousands of different astronomical systems. This is the essential scientific hurdle. Recent evidence. While new theories emerge, what is the latest observational evidence that seems to strongly favor the standard dark matter picture? It is crucial to note that while novel theories emerge, the mainstream evidence continues to pile up in favor of the dark matter paradigm. For instance, a study from 2025 by researchers at the Max Planck Institute for Astrophysics analyzed the smallest, faintest known galaxies, the ultra-faint dwarfs on the very edge of visibility. These tiny stellar systems move their stars so rapidly that the gravity from the visible matter alone is nowhere near enough to hold them together. They should fly apart. Simulations that accurately reproduce the observed stellar motions perfectly match when a dark matter halo is included. Conversely, modified gravity models, including those that adjust gravitational laws on small scales, have consistently failed to reproduce this precise kinematic data without adding some form of unseen mass. This reinforces the idea that something invisible, something massive, is gravitationally binding these systems. For Gupta's evolving constants framework to hold, his model needs to demonstrate how those subtly changing physical laws can produce effects indistinguishable from the gravitational influence of established dark matter halos across thousands of different observed systems, which is a major ongoing challenge for any alternative theory. Future observations. The debate between the evolving universe and the standard dark matter model is likely to be settled by the next generation of powerful astronomical observatories currently coming online. These new instruments are specifically designed to map cosmic structure and expansion with unprecedented accuracy, providing the crucial data needed to test subtle variations in the constants of nature. Leading the charge is the European Space Agency's Euclid Space Telescope, which is busy mapping billions of galaxies to chart how cosmic structures have evolved over time. Equally important will be the Vera C. Rubin Observatory, which, upon full operation, will deliver motion data for a staggering number of galaxies and clusters. offering a statistical picture of galactic rotation far more comprehensive than we have today. These massive datasets will either reveal subtle statistical variations in physical constants that support Gupta's framework, or they will overwhelmingly confirm that dark matter and dark energy remain the most accurate explanations for the observed reality. The next decade of astronomy will be pivotal in this fundamental cosmic argument. Whether Professor Gupta's evolving constants theory proves correct or not, it serves a vital role by challenging our deepest assumptions about physics. If the laws change over time, it rewrites cosmology, validating the structure of an older dynamic universe. Even if it falls short, it forces science to refine our models, ensuring accepted truths are never taken for granted. If you found this exploration into changing cosmic laws fascinating, don't forget to like, subscribe, and hit the bell icon for more radical space science. Thanks for watching Simply Science.